Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 6 of Rectifiers chapter, second chapter that is. So in this lecture, we will study about the full wave rectifiers with R and RE loads. So in the previous lectures, we have been studying about half wave rectifiers, right? We completed the half wave rectifiers and we covered it in depth. We built a basic foundation. Now whatever we analyze, right? We'll analyze them quickly, but it will not go over your head because your basics are clear. As your basics are clear, now you will be by yourself will be able to analyze all this. I don't even need to explain, right? You just pause the video, like whenever I will start the analysis of full wave rectifier. Just pause the video and try to analyze, make the cases and see what will happen. Just for the first one, for the resistive load, you watch me how I analyze it, and for RE load you try to analyze it by yourself. Then obviously you can watch me analyze it, that's fine. Okay, so that will just build up a basic thinking, right? Thinking ability of your brain to analyze, because in the gate examination this standard circuit may not come, something else come, right? So in examination, right, that particular thing will help you, okay, the thinking ability. Okay, so let's first do a bit of comparison with half-wave rectifiers. So unlike half-wave rectifiers, half-wave rectifiers, single phase full wave rectifiers provide lower ripple voltage current, resulting in better performance. So why is that the case? Because in case of full wave rectifier, right, the load always conducts in first half cycle and second half cycle. But in case of full wave rectifier, if only have resistive load, the load only conducts for the first half cycle. In the second half cycle, it is totally off. It is discontinuous. But here it always conducts, and hence it is more it is more ripple free because the load is always conducting. Then single phase full wave rectifiers are also called two pulse converters. Single phase full wave rectifiers are also called two pulse converters. Why two pulse? Because it is conducting for both the cycles, hence one pulse and then second pulse, right? So once we'll see one of the output waveforms, there we'll understand why is it called two pulse as well. Configuration: full wave rectifiers use a bridge configuration consisting of 4 power electronic devices such as SCRs arranged to convert them AC to DC efficiently. So in half wave rectifiers we use only only one device, right? Only one SCR. But in full wave rectifier, if we are talking about bridge configuration, we need to use 4 power electronic devices. So this is the disadvantage. So we need to use more power electronic devices, but obviously you gain some, you lose some, right? And we can use 2 as well, 2 power electronic devices for a center tap transformer. Okay, so that also we'll study. That also I have explained in my prerequisites. There I have explained a full wave rectifier with a center tap transformer where we only need 2 diodes. Known as bridge rectifier, this setup ensures continuous conduction throughout the AC cycle. So throughout the whole cycle, for the positive half cycle and the negative half cycle also, this configuration ensures the continuous conduction throughout right, throughout the load. Full wave rectifiers can also be designed with the help of 2 power electronic devices. This is for what? Center tap transformer. This, like, I have explained this with diode in my prerequisites. Just hold on. Center tapped transformer. Okay, so obviously if you use center tap transformer, there we only need 2, but obviously we need center tap transformer. That is a different device itself, right? That is also costly. So these are drawbacks. Now comparison with full wave rectifier, center tap transformer. So I have talked about, like, I will compare the bridge rectifier and center tap transformer. That I have explained in my previous chapter there. Okay, the peak inverse voltage in a center tap transformer is 2 Vm, whereas in a bridge, right? In a bridge, basically, I can. In a bridge, just hold on. In a bridge, basically, I can say bridge rectifier, it is Vm. Okay, it is Vm. Next, this design requires a center tap transformer which can be bulkier and more expensive compared to a transformer less bridge rectifier. So this requires a center tap transformer, right? So this is a disadvantage because center tap transformer have inductance in them, and if they have large inductance in them, so if they have large inductance, the size becomes very large, and which is not useful for rectifier design, for compact design cases, right? Center tap full wave transformer typically requires 2 diodes, whereas a bridge rectifier only need 4 diodes. So not only the comparison is needs 4 diodes, okay? Like it needs more diodes, but obviously it doesn't need the center tap transformer. The need for the center tap transformer can result in a larger and costlier transformer compared to a single winding transformer used in bridge rectifier. So like a single winding transformer is also used for isolation purpose, but that is very low cost. But a center tap transformer, right, it is a special type of transformer where the tapping is done at the secondary of the center of the secondary winding of the center of the transformer. So that is very costly. Than normal single winding transformer. This machine people can understand. Okay, the center tap transformer can add complexity to the overall circuit design compared to the simpler bridge rectifier comparison arrangement. So generally we use bridge rectifiers only. We don't use center tap transformer. In some special cases we use center tap transformer. Okay, so this is the comparison between center tap transformer and rectifier bridge rectifier design, right? So it has overall 2 configurations. I will not explain the center tap transformer here because that has been already explained in the prerequisite part with the diodes. Okay, so now what are the advantage of a single phase full wave rectifier? Reduced ripple, as explained earlier, of output current and voltage. High load inductance ensures continuous load current without the need of freewheeling diode. We don't need the freewheeling diode. Without it also it will give continuous current. Okay, suitable for which applications it is suitable? It is suitable for moderate to high power ratings in AC to DC conversion, because now it is conducting for 2 cycles, so it is suitable for moderate to high power ratings, and it is suitable for even higher power ratings. Then what we should use 3-phase rectifiers, right? 3-phase rectifiers. Then for even higher rating, okay, that we use in transmission lines. So in normal moderate power ratings we use single phase rectifiers only, full wave single phase rectifiers. For low power ratings, generally less than 200 watts, single phase full wave rectifier with 2 power electronic devices are considered. So this is for the center tap, right? So when is center tap considered? Center tap is considered if the power rating is below 200 watts, then it is viable and economical option. If the power rating is more than some 200 watts or moderate to high power rating, then obviously we have to use the bridge configuration. Okay, bridge configuration. Now let's start with the analysis, right? We'll straight away get into the analysis. So this is the bridge configuration. So this configuration is known as the bridge because this is looking like a bridge, right? This is the bridge configuration, and this is the looking like a bridge. So here I have 4 SCRs instead of a single SCR this time. So you might think that, sir, oh, the analysis will be so difficult. No, right? The analysis won't be difficult if you analyze it in a particular method. So first of all, again, I will totally analyze the controlled and uncontrolled both at the same time. Why? Because if I make my alpha equals to alpha minimum, then the SCR will be converted into basically uncontrolled. And what this can be basically equals to 0. This time alpha minimum is 0. Okay, so we have a pure R load, and let's see, first of all, let's identify the forward blocking mode region, right? What is the period of forward blocking mode? So I will assume everything is off. If everything is off, right, then what I can say, this current is 0. So my VO, right, VO is 0 as IO equals to IS equals to IT equals to 0 amperes. Okay, so my VO will also be 0. VO is 0 volts. So if I apply a KVL loop like this, right, this will be simply equals to VS. So I will start my KVL loop. So minus VS I'm starting from here, plus VT1, then this is 0 drop, right? This is 0 drop. Then here, right, plus VT2 equals to 0 volts. Like I have finished my loop, right? So yeah, this is my loop finished. So now my VT1 plus VT2 equals to Vs. Okay, VT1 plus VT2 is equals to Vs, and I know, right, my VT1 VT2 is some positive value. So Vt1 plus Vt2 is some positive value greater than 0. So obviously both T1 and T2, this will get divided in both the thirisors. This voltage will get divided in both the thirisors. So I can say that my T1 and T2 and T2 are basically what? Are both in the forward blocking mode. Okay, are both basically on the forward blocking mode. Now what about T2 and so what about T3 and T4? So this is what I am talking in the region from 0 to 0, omega t equals 0 to pi for now, because between omega t equals 0 to pi, my Vs is positive. After that, everything will flip. I will talk about that as well. So my Vt2, like if I apply a KVL, right, like this, if I apply another KVL, that if I start from this point, I'm starting from plus Vs, okay, then I'm going through here, finishing this, then again ending at plus Vs, right? So basically, how am I going? Plus Vs plus Vt3 plus Vt4 equals to 0. So Vs plus Vt3 plus Vt4 equals to 0. Okay, so my Vt3 plus Vt4 equals to minus Vs. Okay, Vt3 plus Vt4 equals to minus Vs. Now what I can say? Now basically between omega t equals to 0 to pi, right? This is negative. This is negative. And this is some positive value. So obviously between like Vt3 and Vt4 for the first half cycle, basically it is negative, minus Vs, right? So it will be flipped. And this will always follow. This equation will always be followed. So this will be some negative value. Okay. Then and this Vt1 Vt2 will be some positive value. It will be sine wave because it is the input supply itself. It is getting divided, but it will still be some positive value. I have to get this mode down. I will get this mode down actually. Yeah. Okay, this will be the values. So here, right, my T1 T2 for, as I explained here as well, from omega t equals to 0 to pi, I can say it is in the forward blocking mode. So this is the controlling region, right? So T1 T2 I can control it here. Okay, and for T2 T3, right, I can control it in this region. This is again here in the forward blocking mode. So this region is also control region. Okay, so I can obviously always control two SCRs at once, either leading from 0 to pi or from pi to 2 pi. I can control two SCRs at once, right? So all these things we have understood. Okay, like so I can summarize here quickly things here that my what I can say is during the positive half cycle and the negative half cycle. So my Vt1, am I doing this correctly or not? Vt1 is equals to, okay, just hold on. This is 0 drop, right? If this is 0 drop, what I can say is, okay, yeah, like what will happen is whenever I turn this SCR on, right? So for like whenever I turn one SCR on, what will happen? This whole supply voltage will be negative across this. Why? Because this is 0 voltage and this whole thing will come across this. That's why the maximum peak will be that. I will explain that as well. So whenever like in the positive half cycle, Vt1 comma Vt2 is like Vt1 plus Vt2 is what? Vt1 plus Vt2 is Vs in this case, in our case. Okay, then it is positive, right? It is positive, so obviously this will be in the forward blocking mode. Okay, this will be in the forward blocking mode, and in this case, right, in the negative half cycle, it is less than 0 as Vs is, so we'll write this Vt1 less than 0, it is in the reverse blocking mode, so obviously I cannot control it. And for the second thyristor, VT3, VT4, what will be the case? So VT3, VT4, right? VT3, VT4. Here what I can say is one thing. This is 0 raw, this is grounded. So this is grounded. So this point, yeah. VT3, VT4 I can say is equals to minus Vs. So obviously this whole thing will be less than 0. So this will be in the reverse blocking mode here. And here this will be as like my minus Vs is greater than 0. So this will be in the forward blocking mode. Okay, this will be in the forward blocking mode. So these are the few cases, okay, in which I can control. So in the case 1, I will start from 0 to alpha. Okay, 0 to alpha is the triggering angle at every half cycle. This time, right, alpha is the triggering angle at every half cycle. Okay, half wave. So here when, like, what type of cases there can be here, so here, right, I can trigger this here from 0 to pi for this T1 and T2. Okay, I can trigger the T1 and T2 between 0 to pi, and I can trigger the T2, T3 and T4 from pi to 2 pi. Okay, so from 0 to alpha, these two SCRs will be in forward blocking mode, and these two SCRs will be in reverse blocking mode. Then from alpha to pi, these two SCRs will be on, and these two SCRs will be same reverse blocking mode. Then from pi to pi plus alpha, these two SCRs will be in the reverse blocking mode, and these two SCRs will be in the forward blocking mode. Then from pi plus alpha to 2 pi, these two SCRs will be on, and these two SCRs will be again in the reverse blocking mode. Okay, so this will be the cases. Basically I will have total 1, 2, 3 0 to alpha 4 cases, right? Total 4 cases. Total we will have 4 cases, right? So first case is 0 to alpha. I just explained in the summarize as well, that this time, right, my T1, T2, right, my IS is equals to IT equals to IO equals to 0 amperes, and my VT1 and VT2, right, VT1 and VT2 are greater than 0. They are in the forward blocking mode because I haven't still triggered them. Okay. Okay, so this is the case, and obviously my VT3 and VT4 are obviously less than 0 because those are equals to minus Vs. So it will be less than 0, and they are in the reverse blocking mode. Okay, so like nothing special happens here. Now next, just as at omega t equals to alpha, T1 and T2 are triggered. Now as soon as T1 and T2 are triggered, right, what happens? As soon as T1 and T2 are triggered, these two SCRs turn on. What is my VT3? What is my VT4? So if I apply a KVL, what is my VT3? So I can directly write. Now, like, there was a bit of confusion earlier, right? Now the confusion will be cleared here. So obviously as soon as T1 and T2 are triggered, so my VT1 equals to VT2 as their ideal SCR will be simply 0 volts. So I can apply KVL over here. What will be my VT3? VT3 will be equals to minus Vs. Can apply KVL, right? This minus VT3 minus Vs equals to 0. And this will be same as my VT4 as well. So you can apply KVL here as well. VT4, you can apply KVL here, right? This plus VT4 minus Vs. Okay, am I doing this something wrong? Just hold on. I'm starting from here, plus Vs. Okay, this here, right? So this is the KVL. Plus VT4 plus Vs, and I'm ending at this plus. So I cannot go to here, right? This is not a wire connected. So the wiring is something like this. Right? So this is, I'm starting from here, then going through this point, and then bypassing it, and then ending it, right? So this will be also minus Vs. So this is my VT4. Okay. So now you can clearly understand why is this minus Vs. Previously I wasn't able to explain because all of them were open, so I cannot specifically say exact what values will they be. Okay, but now I can say, right, I could have just said that whether they will be positive or negative, okay, from the previous things I have explained. But here what I can say, I can directly now say everything, right? I can directly now say. So the important point here is that what is my current? So my IO current, right, will be what? So what is my VO at time this time? So if I just apply a KVL, start from here. So I will start from this minus VO. Okay, I will start from here minus VO. Then this will be plus Vs, and this is 0. So I will let it minus. So minus VO plus Vs equals to 0. So VO is equals to Vs, and as I have a simple resistor in the load side, the current will be Vs by R. This will be equals to my 30 second. Why? Because here, right, I am observing that if I apply a KCL at this node, I will apply a KCL at this node. KCL is 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 equals to what? Is equals to this. I will write here. So I will apply KCL. So this KCL is very important. Please listen to me here carefully. This KCL is very important. So I will not go to the case 3 right now. I have to write down more equations. So just copy this, paste this over here. IS is equals to IT1. This IS is equals to what? IT1 minus IT4. Okay, sorry, am I wrong? IS plus IT4 equals to IT1. Yeah, I'm correct only. So IT1 IS plus IT4 equals to IT1, right? So yeah, it will be minus IT4 only. So this is my equation. This is my current equation, right, of the source current. Source current. What can I say about it? I can say, right, I can say that one thing I can say is that this IT4, right, is 0. This IT4 is 0 because obviously SCR is in the reverse blocking mode, no current can flow, right? So this IT4 is 0. So obviously what will be my IS now? My IS is equals to my IT1. Okay, please, like here, right, previously we used to directly write that as there was only one single SCR and everything was in series. Source and load were in series, but now they aren't. So we have to be careful here. What is my KCL at this node? If I apply a KCL at this node, basically IT1 and IT3 are incoming and IO is outgoing, right? So IO, outgoing current, will be equals to incoming current, IT1 plus IT3. Again, the interesting fact here is that IT3 is off. Okay, thyristor T3 is off. So this will be simply 0 amps of current. 0 amps of current. So basically my IO will be equals to my IT1, which is equals to IS. So IO is IS right now, okay, which is equals to Vs by R. Okay, so now this is plus, this will change also as well, right? Another important thing is that what is the maximum value that my current get to? Okay, what is the maximum value? So if just I will write this case 2. What can I say? If my IO, like what is the maximum value that can through the load that can flow? It can have two cases again. It can be Vm by R if my alpha is less than pi by 2. Why? Because if my SCR is triggered before pi by 2, right, voltage will go up to Vm and then it will reduce. So the maximum, like, current will be when the voltage is maximum. But if my IO, like IO, I can write here directly, right? It is Vm sin omega t but yeah, Vm sin omega t bar. So if my alpha is actually greater than pi by 2, and less than pi, what will happen is that the maximum voltage that will come across the resistor will be Vm sin alpha, because after pi by 2, right, the sine wave only reduces from Vm. So the maximum voltage will be Vm sin alpha, and after that it will reduce, so maximum current will also be Vm sin alpha. And here, right, what is the direction of the power flow? Direction of the power flow is from source to load, right? Direction of the power flow is from source to load. So things are pretty simple. It is a resistive network, so we don't need to give it a much thought. Then from again pi to pi plus alpha. Pi to pi plus alpha, like if I analyze this here, right? If I analyze this here, what is my VT1 and VT2? VT1 and VT2 are actually equals to this Vs only, right? Actually equals to this Vs only, because what will happen is that this output voltage will try to go to negative and it will try to flow some negative current, right? Direction of current will reverse because VO, the polarity of VO will be reversed and direction of current will be reversed. Hence, this SCRs will again go to natural commutation. So at omega t equals to pi, because the current reduced to 0, right? Current reduced to 0, they went to natural commutation. Again, it tries to go to negative because VO is equals to Vs. Okay, VO is equals to Vs. It tries to go to negative. Hence, current tries to flow in this direction. Okay, which is not possible. So at omega t equals to pi, natural commutation. T1 and T2 are naturally commutated. Okay, naturally commutated, right? So that's fine. So they turn off. Now what happens is, again, if I measure VT3 and VT4 will be again negative, right? VT3 and like VT4 will be less than, not less than, VT3 and VT4 will be greater than 0, because what, they are equals to, like the addition of them are plus minus Vs. So the negative of minus Vs will be positive because Vs itself is negative right now. Vs itself is negative. Okay, so these will be in forward blocking mode and my T1 and T2 are natural commuters, so they are in reverse blocking mode. Things are simple, and my output voltage this time, right, VO is equals to IO into R, and I know my IO is 0 amperes now. So IO is 0 ampere, and so is the source, right? IS is also 0 ampere, because why? Because no current is flowing through here and no current is flowing through here, so all of this IS current will also be 0 amperes. So did I write this in the case 1? I'll just quickly check. Okay, this is not the case 1, this is the case 1. Okay, yeah, all of them are 0 amperes, but you need to understand why are they 0 amperes. And like I forgot to write the VO as well here. Okay, I forgot to write the VO. So VO, right, will be 0 volts right now, because VO is IO into R. So this will be 0 volts. Okay, next what will happen? This is case 3. So now let's come to the case 4 here, right? Here at omega t equals to pi plus alpha, my T3 and T4 are triggered. T3 and T4 are triggered. Okay, so this is the case now. So here what will happen is T3 and T4 are triggered, and as I told you, right, they are in forward blocking mode, so they will instantly turn on. So I can directly write a KVL now for this SCR T1. So what will be my VT1 plus VT1 will be equals to plus VT1 minus Vs equals to 0. So plus VT1 minus Vs equals to 0. VT1 equals to plus Vs, right? And what is my Vs? Vs in this region, right? Vs in this particular duration is negative. Vs is negative. Vs is less than 0. Okay. So hence obviously VT1 is this, and like if you apply the KVL, VT2 will also be the same only. VT2 will also be the same. Hence both T1 and T2 hence proved are in reverse blocking mode actually. And obviously they are triggered. So what is my VO this time? So if you apply KVL now, right? If you apply the KVL through T4 and T3, so I will start from here, plus Vs, okay, I'm going, plus VO is equals to 0. So plus Vs plus VO equals to 0. So this time, right, my VO is equals to minus Vs. So you will say, sir, how is negative voltage coming? Current cannot flow in reverse direction. But the interesting fact is my Vs is less than 0. As my Vs is less than 0, so this VO overall becomes positive. VO becomes positive. Hence current is still in this direction only. Current is still in this direction only, right? So everything is fine. Current can flow in this direction. Everything is fine. Again, this is fine. So what is my? I will take another page. I will compute the currents now. So my VO is equals to minus Vs. So my IO is equals to minus Vs by Vs by R, which is equals to minus Vm sine omega t by R. Okay, the same expression as I got previously, but just a negative sign so that overall it becomes positive because omega t is between pi plus alpha to 2 pi. Now what about my IS? I can again apply KCLs. IS equals to, I apply the previous KCL, that IT1 minus IT4. This time, right, my IT1 is 0 because this is off. So my IS is equals to minus IT4. IS equals to minus IT4. And what is my IT4? I can apply a KCL here, right? My IO is equals to IT4 plus IT2. Okay, so again, right, this IT2 is 0. This IT2 is 0. As this IT2 is 0, what can I say? My IO is basically IT4. Okay, and if I replace this here, right, this will be minus IO. IS this time is minus IO. Okay, it is not IO. It is not equals to IO, it is minus IO. So previously it was plus IO, now it is minus IO. If you just observe the analysis of the previous cases, right, of the case 2. So what is my IO? IO is minus Vm sine omega t. If I do another minus, this will be Vm sine omega t by R. So overall, right, like what can I say is that IS is negative because this Vm sine omega t is actually negative. Okay, but IO is positive. Okay, so the biggest advantage is 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 negative, and IS is negative, I can understand IS is negative, and my VS is also negative. If IS and VS both are negative, what can I say? Just hold on. As my IS is also negative and VS is also negative, again the power, right? Power is greater than 0 because negative times negative is positive. So power flows from source to load only. Power flows from source to load only, right? So this is the power flow. This is from source, this is from load. Okay. Right? This is the flow of power. So this is the case. This is the case which happens in case of the second half cycle, and this cycle will repeat again. This cycle will repeat again, and this will be the waveforms. So the most important part is my IS, right? My IS is not exactly equals to IO. IS is equals to IT1 minus IT4 and IT2 minus IT3. You can derive with that KCL as well. And what is my IO? IO is also a bit different right now. IO is a bit different. So IO, right? IO you can see in this case IO is IT1 plus IT3. So just write my IO as well. IO is IT1 plus IT3. So IT3 will come across here. And it will be IT2 plus IT4. So if you observe here, right, it is IT2 plus IT4. So IO is this as well. So things are different here. So you can observe, like, why have I drawn this both VS, and this is what? This is minus VS. This is plus VS only. Okay. This is plus VS. And this part, right? This part is simply minus VS. Okay. So this part is plus VS and this part is minus VS. Why have I drawn it? To simplify things. Because for the first half cycle, right, the output will follow positive side of voltage, and for the next half cycle the output will follow the negative VS, right? So negative VS is for the next half cycle is actually positive, so it will follow this part. So it will always be positive from alpha or pi plus alpha. Like you just watch the waveforms and you can cross verify, you will understand. And VT1 and VT2 in the duration from 0 to alpha, right, are in the forward blocking mode, so it will block the voltage, and T3 and T4 are in the reverse blocking mode, so they are coming across a reverse voltage and they are coming across a forward voltage. I hope you understood this thing. Now just as these are triggered, as like here in this region, right, all are off, everything is off. Okay, just as they are triggered, what will happen? The voltage will instantly go to 0, and this will still be in the reverse blocking mode now. So voltage will instantly go to 0, and like it will be on. T1 and T2 will be on in this division from alpha to pi, and then after that again all will be off, and then again from pi plus alpha to 2 pi, T3 and T4 will be on and others will be off, right? So this will be the voltage equation across the 30. So this will be the current equation. So current equation is always positive. It will just be the proportional to the voltage. Voltage is always positive because the voltage is getting flipped during the negative half cycle. And this IS is also, now interesting fact is IS, right, in this region is equals to plus IO, and in this region is equals to minus IO, as derived here as well. As I derived here as well, that IS is equals to minus IO, and in the case 2 you could have seen IS is equals to simply IO. So it will follow IO during the first half cycle. During the next half cycle it will follow minus IO. Okay, then this is what, this is the thyristor current. Thyristor current will be on for the first half cycle, and thyristor current can only be positive, it can never be negative. That's why you will see it is always above the x axis. So it is always positive, it is always positive here, right? Thyristor current is 0 because they are off, but again it is positive because they turn on, right? So these are the waveforms. Okay, and the derivations, this results are pretty simple, right? What is the average output voltage? You can do the simple integration. This I have proved previously as well. So simple integration you can do from alpha to pi, and you will get back this expression, right? And like what is the average output voltage for a full wave rectifier compared to the half wave rectifier? So it will be twice, right? Why it will be twice? Because I'm conducting twice. Okay, previously I was only conducting from alpha to pi. In case of half wave rectifier, now I'm conducting from alpha to pi as well as pi plus alpha to 2 pi. So for two regions I'm conducting twice. So obviously output voltage will also be doubled in than half wave rectifier. So it is more advantageous. IO average is simply VO average by R. So exactly that formula only. And VRMS, previously my, like this point is important, right? This point is important, that previously my cycle was like here. Previously my cycle was 2 pi, but now my cycle has changed to pi. Why? Because if you observe, right, I'm repeating after pi time period. So obviously my time period will be pi now. So that's why I'm dividing by pi. And why is it called 2 pulse? Why is it called 2 pulse converter? Because for a total cycle of the input, I am getting 2 pulses. Okay, 0 to pi and pi to 2 pi. Okay, so that's why these are the things that I am getting. That's why this is called a 2 pulse converter. That also will come to. And RMS value we can derive. This is homework for you. Just derive by your own. That this, like I've already derived for a few other homeworks. Okay, you can derive by your own, right? This just, you are going from alpha to pi. That's it, right? So in case of RMS, right, the half wave rectifier, the full wave rectifier RMS value is root 2 times the half wave rectifier. So don't need to remember this. Okay, just understanding the derivation is enough. Don't need to remember all this, right? So like I'm comparing between the controller and uncontrolled. For alpha equals to 0, the average output voltage, right, will become 2 Vm upon pi. So you put here alpha equals 0, this will become controlled one, uncontrolled one. So this will be 1 plus 1, 2 into Vm by pi. Okay, and what will be my VORMS? VORMS will be Vm upon alpha. If I put alpha equal to 0 to 11, this will go to 0. This will be pi. This will be 1 by 2, and this will be under root 2 into pi. So under root pi and under root pi will get cancelled, and this will be under root 2 Vm by under root 2, and that is also true, right? Why? Because basically if I square the negative of Vs, right, it will be simply square root of the positive as well. So everything becomes positive if whenever I square everything. So this will be still positive, right? So that will be only same only. So yeah, that's why. So this will be Vm by root 2, same as the supply. Okay, same as the supply. Ripples, this formula you can, obviously this formula you can remember, and that's it. Like you know how to derive VO RMS, VO average, you know how to derive this, and you can compute the ripples for all this, right? And efficiency of converter is again VO DC upon VO, like PO, sorry, PO DC upon PO, and it will be VO square average by R divided by VO square RMS by R, and you can compute all this. Just if you put alpha equal to 0, you will observe you are getting twice the efficiency. Previously you were getting, I think, 40.5 efficiency. Now you are getting 81% efficiency, much better, right? Because your VO and IO both have increased. VO RMS and RMS both have increased by root 2. So overall the power increased by twice. That's why. Okay, so these are the things. So and also one more thing is that my power, right? Power is always positive. As my power is always positive, that means what? That means that power can only flow from only flows from load to source. Okay, power only flows from load to source. This is the case. So that is the case, and my sorry, not load to source, I am taking the opposite thing. Power only flows from source to load, right? And in case of ideal converter, my PS, whatever power I delivered from the source, that will be equals to PO, whatever the output got the power, if the converter is ideal. Why am I telling this? Just for derivation of power factor. If converter is ideal. Okay, so ripple frequency is simple only here, right? Obviously what is the frequency of the output voltage waveform in terms of supply? It is 2, right? Because the cycle has reduced, time period has reduced by half, so obviously frequency will increase by 2. So my N, in this case, N will be 2. Okay, that's why this is called a 2 pulse converter. Okay, now here, right, let's come to the supply parameters. My Vs will be this, Vs RMS will be this, my IS average will be equals to IO average? No. Okay, because my IS is not always equals to IO, right? My IS is not always equals to IO, and my best thing is my IS average is actually equals to 0. Why? Because for the first half cycle it is plus IO, and for the next half cycle it is minus IO, and overall the shape of the waveform is same, just it is negative. So overall the average value goes to 0, and this is very good, right, for the supply side. Why? Because I don't have any DC component, because supply side is AC and it doesn't like DC component. It is the worst harmonic. So obviously I am very happy now that I don't have any DC component. No DC. How do I make up a space? No DC component. I am very happy. Okay, super happy. So no DC component on the supply end, that is good. I am getting conduction for whole cycle on the load end, that is also good. And RMS value, but RMS value will be same, right? RMS value will be same because it is like minus IS minus IO whole square and IO whole square are the same thing. What is it? It is IO whole square, because minus into minus becomes plus. That's why the RMS value will be same, but the average value won't be same. Okay, so I hope you understood. Cos phi s equals to PS by SS. It is equals to output power by the apparent power. Why? Because I am assuming that it is ideal converter. So ideal converter, if it is not right ideal converter, they will tell the percentage by which it reduces the power. Okay, so this is VRMS by R, and like you can convert this into other forms as well, right? Other forms as well. Okay, but here, right, what will happen is that VRMS by VRMS square by R, you can write this as IORMS square into R as well, you can write. Okay, so all those things you can write, so you can do it. Now what is the conduction period? Conduction period is on period, same as in the half wave rectifier, pi minus alpha by omega, okay, is the conduction period. And what is the natural commutation time? Pi by omega for the other two thyristors, right? And what is the peak inverse voltage? So peak inverse voltage that anything can get, right, this thyristor can get, is obviously this minus Vm, right, minus Vm, okay. That is the peak inverse voltage that any thyristor can come across. It cannot come across any more voltage, so it will be minus Vm, okay. That will be the peak inverse voltage. And thyristor current, so thyristor current, right, they will conduct, and there will be some positive value. They, and T1 and T2 are always conducting for the first half cycle, and T2 and T3 and T4 are conducting for the next half cycle. So here, right, the time period of the thyristor current will be 2 pi. Why? Because thyristor current is repeating after every 2 pi, because there are 4 thyristors and 2 thyristors are conducting in one cycle and 2 thyristors are conducting in other cycle. So overall the repetition is only 2, time period is only 2 pi. It is repeating after every 2 pi. So if you just use this formula, you will find out the average value, that is divided by 2. Whatever average value you have found out, IO average, that I will just divide by 2. So this, right, this will be equals to IO average divided by 2, because it is obvious that it is only conducting for the first half cycle. So it is IO average divided by 2. Okay. Next, RMS will be basically root 2 times divided by root 2 times. Or yeah, why? Because the area has been halved, so it will be divided by root 2 times. Because you can see here, right, you can see if the area is half, then it will be divided by root 2. So if you observe the RMS current, this is root 2, right? So here root 2 R will come, so it will be root 2 times. I will write the relationship. If you study signal systems, they will understand why is this root 2 times. So this, right, this will be equals to I over RMS divided by root 2 simply. Okay. So like there are few groupings here. This 2 groups are known as common cathode, and these 2 groups are known as common anode. Okay. Anyways, I know these two SCRs conduct simultaneously with each other, and these 2 SCRs also conduct simultaneously. But these 2 SCRs never conduct with each other. Why? Like here we will read about the groups. Current flow in the upper group. The SCRs in the upper group carry current from source to the load. Source to the load. Okay, source to the load. Current flow in the lower group. The SCRs in the lower group carry current from the load back to the source. So that's why they are grouped. So the out of these 2 SCRs, right, one of the SCR will be on, and current will flow from the source to load. And out of these 2 SCRs, one of these SCRs will be on, and current will flow from what? Load to source. Okay. So these 2 SCRs provide the path for load to source, and these 2 SCRs provide the path for source to load. So that's why like these are grouped like this. This is common anode and this is common cathode. Okay. So these are just the name notations. That's it, right? So there is one question. So you try to solve this question. You have to draw the output voltage waveform for the below circuit. So this is very interesting question. So this is like there are 2 circuits here, A and B. Try to solve this by yourself, and then I will come back, and then we will also analyze the RE load. So what is happening in this figure A, right? In this figure A, if this switch is closed, then at t equals 0 I am closing the switch, and I have a positive voltage here and then like some negative potential here, right? So this positive is connected with this P and negative is connected with this N, right? So this will not turn on because this positive is connected with this N, so this will not turn on. And here, right, this is already on. If this is already on, what will happen is that if I apply simple KVL here, this is satisfying the loop, right? This is satisfying the loop. So what will happen? The supply will be short circuited. So supply will be short circuited, and this point, right? This point will be totally same, and this diode will not be on anymore. Okay, so this diode will not be on because this point is plus and this is on, right? This is on. So overall, what is happening is that if I just copy this circuit. Here if I just copy this circuit, right? So here I am getting some plus voltage. Let's just start omega t equals to 0 plus, and here, right, this is closed. So if this is closed, this point, right, this what is like here, right, this loop is getting completed. So what I can say is this diode, let's name this as D1. D1 is on. Okay, D1 is on, and supply is getting short circuited. supply is getting short circuit. That means what? That means that no current flows through anything else, right? Supply is getting short circuit. That is very dangerous. This is also a type of fault, right? This is also a type of fault. These type of circuits we should not design. This condition should never be present in our circuit for the circuit to be stable. This circuit is becoming unstable because supply has been short circuited. If supply has been short circuited, then there is no current flowing through this, right? Because these 2 points are shorted and this is on. So supply is totally short circuited. So no current will flow through this, right? No current will flow through this. So my output voltage will be simply 0 for the positive half cycle. Okay, for the positive half cycle. So VO is 0 for the positive half cycle. Then what happens next? As soon as this becomes negative, right? This, like, I will assume, like, now I will write the plus sign here. Okay, cross this up. As soon as this is going negative, that means the plus sign is here and minus sign is here. Now, right, the minus sign is connected to this P, okay, and this plus sign is here. So this will not turn on, but this will turn on, right? This minus is connected to this N, and this is already on. I don't care about this. So this is on, right? There is a pathway of current to flow. Okay. In this case, right? In this case, in which path can the current flow? The current can flow in this path, okay, in this path, or in this path. Okay. And this diode is off, right? Because plus is here, so this diode will be off anyways here, because this is higher potential and the cathode is connected to the higher potential, so this will be off. So current can possibly flow only in this direction, okay, in this path. Now the problem is, if current wants to flow in this path, right, current has already this path to flow. This is the least resistive part. To reach to this negative terminal, right, it has to either come through this resistor or it has to come through this 0 ohm resistance. So it will choose this. It will not choose this. It will only choose this. Like if I draw this circuit, even if this diode, let's say if I turn this diode on, right, even if I turn this diode on, okay, what will happen here? What will happen? If I name this node as O, okay, this node is O, this is O, okay, and this is O. So what is happening? This R, right, this R is connected between O and O, and this is totally short circuited. So this R is totally short circuited. This is irrelevant. So if I apply a KVL over here, what is the KVL? So this KVL is what? IO into R equals to 0. So R is not 0, so IO will be 0. So from here also, from this KVL also, you can understand why the IO current is 0. Even if this diode is on, then also the current will be 0. Okay. So you understand, even if this diode is also on, then also the current will be 0 only. Okay. No, then there will be pathway of current, but that we will understand here. Okay. So this diode is not turning on because this is connected to the cathode. So here this is connected to the anode. So this diode will be on, this diode will be off. So if this diode is off, that means, this diode is off and this diode is on. So now if I apply a KVL, right, now if I apply a simple KVL, okay, and this diode is off, right, so if I apply a simple KVL, my I will go through this will be what? So these signs are here just for the understanding sake, but this is what? This is Vs, right, and this is like the initial actual polarity was this, like this, plus minus Vs. The actual polarity, initial polarity was like this. So I will go through this, plus Vs plus VO will be equal to 0. I'm applying my KVL like this. Okay, so my Vs is equals to, my VO is equals to minus of Vs, right? VO is equal to minus of Vs. So how will the output voltage waveform look like? The output voltage waveform will look something like this. VO is this. So obviously from 0 to pi, this will not be on. Basically the diode, like the output current is 0. Then from pi to 2 pi, this will follow the input, basically negative of the input, to remember, because the input is actually negative and negative of negative becomes positive. So this is from 2 pi to 3 pi, okay, and this is my Vm. So this is what the output voltage will look like for the part A of this question, and we avoid this. Okay, we don't want this. I'm teaching you because if you see some kind of condition like this, you will obviously have to redesign your circuit, right? Avoid this at any cost. Avoid this at any cost. Now let's come to this one. This one is like simpler if you understood this one, the previous one. Because why? Because here if you see that if these two switches are closed, right? These two switches are closed. Supply is always short circuited. Supply is always short circuited. Because for the previous case, right, supply isn't always short circuited because for the negative half cycle there is a path for this current to flow, because there is no path for this current, right? This diode will be off. But here what is happening? Supply is always short circuited. Supply is always short circuited. So even if you turn this diode on, right? If you turn this diode on, what will happen? Okay, I went here. If you turn this diode on, this is what? Again, VO is 0. If you turn this diode on, okay, you apply a KVL loop through here, again VO is 0. Okay, so obviously VO is 0. And another thing is the supply is always short circuited, which is very, very dangerous because infinite amount of current will flow. Because this generally they have some finite resistance, this switch is very low, and due to that low resistance, VO by R is low, so current will be very high. So supply is always short circuited. Okay, supply is always short circuited. Very bad. Okay, very bad. And this is always 0. Always 0. So my VO will be what? Simply 0. Always. Sorry for the interruption. Actually, I had to go and have a haircut because that was urgent, and I wasn't getting time, so had to do that. So I had to pause in between the recording. So now we'll understand about RE loads for a full wave rectifier. The analysis through a RE load. So theme will be same, but here I will explain a bit like differently, and also in the previous case, right, with pure R load, there also I will like quickly summarize whatever we learned because I just made a bit of tweak. Okay, so here, right, one thing is for sure, this is that I will study controlled and uncontrolled rectifier both in the same analysis. What I will do, just instead of alpha, right, if I replace alpha with alpha minimum, in this case it will be theta, our converter will be uncontrolled one. Okay, so first of all, how to start the analysis? Same, right, when all the devices are off, then what is my forward blocking region, that we have to identify. So in this case, right, I can easily identify that by, if all the devices are off, right, if all the devices are off, then I can say that what is my VT1 and VT2. So if I apply a KVL through this loop, because current is 0, right, if all the devices are off, I know current I of t is 0. So if I of t is 0, then if I go in this route, right, if I go from this route, that it will be plus VT2 minus Vs plus VT1 then plus E, because I into R is 0. So I can say that VT1 plus VT2 equals to Vs minus E. Okay, VT1 plus VT2 equals to Vs minus E. So this is the case when all the diodes are off. Now here, right, when will this voltage be negative? When Vs is less than E. And when will this voltage be positive? When Vs is greater than E. So when will my T1 and T2 thyristors be in the forward blocking mode? When this is greater than 0, right? Because my VT1 and VT2, they at max can be what? They at max can be equals to 0. Because as soon as, or like if they are practical, there will be some on voltage. At max they can be that voltage. But as soon as this potential becomes positive, right, they come into the forward blocking mode. Okay, sorry, there can be some positive voltage as well, because they will be in the forward blocking mode. I'm sorry for that. So like, what is the region of forward blocking mode? The region of forward blocking mode is, because here, right, my sum is positive. So what will happen if I assume the two thyristors to be identical? Then I can say that they will divide voltage equally. So if I assume, so many teachers, right, they don't explain this part. I will explain this here carefully. So assume thyristors are identical. If thyristors are identical, there will be a leakage current flow, and due to the leakage current flow, at the VI characteristics, the voltage drop will be some voltage VT, and that will be same because I assume that two thyristors are identical. Okay, due to that reason, assume T1, T2, T3 and T4 are identical. Okay, so if I assume that, then I can say that VT1 will be equals to VT2 will be equals to Vs minus E divided by 2. Now when will be this in the forward blocking mode? This will be in the forward blocking mode when my Vs minus E divided by 2 is greater than 0. So when is that case, that is basically sine theta, not sine theta actually, theta is greater than sine inverse E by Vm. Theta is greater than sine inverse. Okay, sorry. So at this point of time, they will be in the forward blocking mode, both the diodes, right? So here, after theta, they will be in the forward blocking mode, and here, right, pi minus theta also, they will again come back to reverse blocking mode, because then again my Vs will be less than E, and then again the voltage will be negative. The sign of the voltage will be negative for both the diodes, both the thyristors. Hence, they will be again off. Okay. So similarly, you can do it for the this case as well. T3 and T4. You will see at what is this point? This point is pi plus theta and 2 pi minus theta. The thyristors will be in the forward blocking mode, and for the rest, right, it will be in the reverse blocking mode. This value is E. Okay. So this was the analysis when all of them are off, and we got to know the forward blocking mode and the reverse blocking mode. Now let's, okay, this is already done. Like this was for the T2 and T3. Okay. One important point to note here is that let's say I have triggered this here, right, in the forward blocking mode. In the forward blocking mode for T1 and T2, I have triggered this here. So SCRs gets turned on. So I will assume that T1 and T2 are on. SCR are triggered. So when T1 and T2 are on, right, then what is the situation? Then the voltage across the reverse voltage across the thyristor is actually different. It is not the same as when all of them are off. So when two of them are on, these are known as the natural pairs. So sometimes the terminology is used for this T1, T2 or T3, T4 as natural pairs, because when like current flows, right, then one natural pair has to conduct. So this is one of the natural pair where these two SCRs are on. And when current flows in the negative cycle, then these two thyristors are on. Okay, these two are known as the natural pairs. Okay, so here, what I can say this as, when this is on, right, when these two are on, then I can simply apply a KVL. Start from here, plus VT4 plus Vs, then I can go here and end here again, right? I have completed a loop. So the KVL will be plus VT4 plus Vs will be equals to 0. So this time, right, this time my VT4 is not by 2, because both the diodes are not equally blocking, right? This time my VT4 is V minus Vs directly, and I can safely say that this will be less than 0. Hence my T4 will be in the reverse blocking mode. It will not turn on. Okay, there is a simple E and R load. There isn't any inductive load, so that cannot turn on this thyristor, right? So like why is this negative? Because Vs is positive. I'm in the first half cycle. In the positive half cycle, right? In the positive half cycle, Vs is positive, hence minus Vs will be negative, and if minus Vs is negative, Vt4 will be also negative. What about Vt3? You can apply the same KVL, right? You can start from here, plus Vt3, then this is 0, then this is plus Vs, and then again I end over here. So Vt3 is also equals to minus Vs. Okay, so this is also less than 0. This is also less than 0. Okay, so what can I say? My T3 also is reverse in the reverse blocking mode. Okay, T3 also is in the reverse blocking mode. So again, for another case, that is for the negative half cycle. For the negative half cycle, and let's say I have triggered my SCR, T3 and T4 are on. T3 and T4 are on. So here, right, what will happen is this is in the negative half cycle, and in the negative half cycle only my T3 and T4 can be on, because they at that period only they are in the forward blocking mode. Obviously, all of these are this is not a inactive load, so I cannot control anything with the load, right? With the load. Okay, so here again, if you apply simple KVL, right? If you apply simple KVL, minus Vs plus Vt1 equals to 0. So Vt1 equals to what? Vt1 equals to not 0, Vs plus Vs, right? Now you might say, sir, Vt1 is positive, then no. Here, right, I am in the negative half cycle, so my source itself is negative in value, so this will be something 0. This will be something 0. Okay, and same for Vt2. Vt2 will be also Vs, and this will be also negative. So these two are negative. That means what? That means basically these two are in reverse blocking mode. Okay, these two are in reverse blocking mode. So that is the case, and like this is from, I will just write the range, else people will get confused. This is from pi to 2 pi, and this is from positive half cycle, means 0 to pi. Okay, so I hope you got the point that what is actually happening over here, right? So my thyristor voltage is not always equals to Vs minus E. It is equals to Vs when it is reverse in the reverse blocking mode. When two of the thyristors are on. If all the 4 thyristors are off, then that means what? No current is flowing. If no current is flowing, my voltage is simply Vs minus E then. Okay, so you have to take these things in mind. So now actually start with the analysis of the converter. So the same thing you should do in the with pure AC load, because there I haven't explained this in this much of depth, but then I thought I should explain this, because many educators, what they do is they don't explain this part. They just directly go, okay, in this case 1 this will be on, this will be on, in case 2 this will be on, this will be on. That's it. That's the analysis. But they don't actually explain you what is happening inside the converter, because if you don't understand what is happening inside the converter, then in the next day if some difficult question comes up, right, you won't be able to solve it. So it is very important to understand what is happening inside the converter. Now let's start with this. So here, right, case 1 is from 0 to omega t equals theta. So in this case, right, what is actually happening? My Vs is less than E. My Vs is less than E. So if my Vs is less than E, that means everything will be off, because either it will be like it can't be in the forward blocking mode, everything will be in the reverse blocking mode. Okay, why? I will just explain. So if Ia is equals to I will assume everything off, and then I will prove with respect to the voltage that it is actually true. I is equals to IO equals to IT, all the 30 seconds are 0 amperes. So what is my VO? VO is simply IO into R plus E. So it is simply equals to E, because IO is 0. Now what is VT1 plus VT2. So VT1 plus VT2, right? If you apply simple KVL, like I just derive, if we have all the devices of VT1 plus VT2 will be simply Vs minus E. Now this is the assumption, right? My Vs is less than E. So VT1 plus VT2 will be something less than 0. Okay. As it is less than 0, what does it mean? It means they are in the reverse blocking mode, both. Because both will, like if they are identical, then both will equally block the voltages. So it will be Vs minus E by 2. Okay. Then next case, what is happening is from theta to alpha. From theta to alpha is that my Vs is greater than E actually. Vs is greater than E. So Vs is greater than E. What is the value? So again, I will assume all of them are off. So IO equals to IS equals to IT equals to 0 amps of current. So again this time my VT1 plus VT2 is Vs minus E if you apply the KVL. But this time, right, the difference is Vs is greater than E. So if Vs is greater than E, if I just rewrite this inequality, Vs minus E will be greater than 0. So I can say that VT1 plus VT2 will be greater than 0. If this is greater than 0, that means what? This will be forward blocking mode. Okay, this will be forward blocking mode. So like what is my VO? VO will be E, right? VO will be simply E. VO won't change. So still it is off, but right now it is in the forward blocking mode, and previously it was in the reverse blocking mode. Here I had no control, but here I have control. I can turn it on anytime. I will turn it on at alpha, at omega t equals to alpha. So at omega t equals to alpha, SCR is triggered. Okay, SCR is triggered. Just let me check one thing. Yeah, at omega t equals to alpha, SCR is triggered. So if LCR is triggered, so these two, right, these two will turn on, T1 and T2, because they were in the forward blocking mode. These are like you can derive, right? This VT3 plus VT4 will be minus Vs plus E, I think, something like that. So they will be anyways in the reverse blocking mode. In this case, in second case as well, in first case as well. Okay. So if these two turn on, right, what will be my VO? You can again apply simple KVL. Your VO will be simply Vs. Okay. So if these two are on, VO is Vs. And here, right, if you just write down the currents, like your IS will be equals to what? This IT1 plus IT4. IT4 is 0. So it is equals to IT1 equals to what? Here, right, this incoming and this is also incoming. But IT3 is 0, right? So whatever is incoming here, that is outgoing. IO is outgoing. So this is equals to IO. Okay. So this is the current. And what is the value of the current? IO. I can write it here itself. It is simply Vs minus E by R. And you can write the two expressions for current. What is the maximum peak voltage? That depends, right? That depends where am I lying at. So IO max, right? Peak value of current. This can be asked in questions. Okay. This is equals to what? This is, there can be two values here. One is Vm minus E divided by R. Another one is, okay, this is not looking that great. Vm sin alpha minus E divided by R. So here, right, here what will happen is that my alpha will be between 0 to pi by 2. That's why, like, I will not encounter the peak voltage. Peak voltage I will encounter after turning on the SCR. But here, right, I go, like, the peak voltage has already been occurred and I am passing after pi by 2. So whatever the voltage that I get, right, just at triggering, that will be the maximum voltage. That's why the current will also be maximum at that point of time. So alpha is between pi by 2 to pi. Okay, so these are the things. So here, like, power will always flow from source to load, because here I have only a battery, right, and there is no inductor to store the energy and flow it from load to source. That is not possible. Now here in this case, right, from pi minus theta to pi plus theta, what is happening? From pi minus theta, right, natural commutation is happening. Natural commutation. Why natural commutation is happening? because current, right, I is equals to 0. Here if you see that this is what this value is when my Vs equals to E. So what is the expression for IO? IO expression is Vs minus E. So when Vs is equals to E, this IO becomes 0, and if once this IO becomes 0, the SCRs are naturally commutated, they are turned off. So basically my Is equals to It equals to IO equals to 0 amperes. What about VO? Whenever the current is 0, right? So VO becomes E. Okay, IO I have already proven, and like yeah, at this value they turn off. So yeah, that is basically what is happening until pi plus theta. Then after pi plus theta, what will happen? Again here, right? They will move to forward blocking mode, which thyristor. So if I apply KVL, for this, let's apply KVL for this. So we'll start from here, plus VT3 plus Vs plus VT3. Okay, and then this is plus E equals to 0. So plus VT3, okay, I started with VT4, right? Yeah. VT4 plus VT3, then this I started with, yeah, okay, plus Vs was also there, sorry. So this is plus VT4 plus Vs plus VT3 plus E equals to 0. So this will be what? So my VT4 plus VT3 will be equals to minus of Vs minus E. Now what do you know is that Vs is, so in this, right, after theta, pi plus theta means what? Pi plus theta means what? Again my Vs is greater than E. Okay, again my Vs is greater than E. So that is fine. So if I take this V on that side, that will that no, that won't be helpful. Okay, sorry, actually in this pi plus theta, right, what is happening in this region is Vs is actually less than minus E actually. Why? Because here, right, in this region, like if I just draw this minus E as well, if I just draw, like this is the minus E, right, this is the minus E actually. Okay, okay, this is actually already minus Vs, that's why the confusion is coming. Okay, so here, right, this is my actual Vs waveform. So where will the minus E lie? Minus E will lie here. Okay, and my Vs is less than minus E. In pi plus theta, Vs will be less than minus E. Why? Because as I increase, like let's say this is pi plus theta, right, and here there is minus E. So as I increase my pi plus theta, what will happen is that it will go more lower than minus E, and hence what will happen is that it will come into forward blocking mode. Why? Because if you observe here carefully, that Vs is this, right? So when does VT4 and VT3 need to be in forward blocking mode? When this is greater than 0. So overall this has to be greater than 0. So if this has to be greater than 0, how is it possible? My minus of Vs, or I can say Vs plus E must be less than 0, which is exactly this condition, right? That is my Vs plus E is less than 0. So this is actually correct, and this was actually correct. So is it actually happening? Why? Because here you might say there is minus E, Vs and minus E, this will be total negative. How can this be in the forward blocking mode? Because Vs in itself is negative. Vs in itself is negative. That's why, what is minus Vf? Minus Vs is just some positive in the negative half cycle, that is from pi to 2 pi. So that's why I always plot here minus Vs and then I compare with respect to E. Okay, that is the reasoning behind that. So if I plot minus Vs, all the confusion goes away, and if I compare with respect to E, right, just after pi plus theta, my minus Vs will be greater than E. Okay, minus Vs or plus Vs will be lower than minus E, any one of them. Okay, any one of them you can choose. So here this will be the case, this will be the answer, VO will be equals to E. Okay, so now let's start with the case 6. So I can safely say that my thyristor T4 and T3 are in the forward blocking mode. Then again at omega t equals to pi plus alpha, omega t equals to pi plus alpha, what is happening? My T3 and T4 are triggered. Okay, so here what I can say, basically whenever they are triggered, right, my VO will be equals to what? This time if you apply KVL, VO will be minus VS. So if I go from here minus VS, then okay, sorry, if I go plus VS and plus VO equals to 0. So VO will be equals to minus VS. This is a very important, and as VS is negative, right, hence my overall VO will be positive because VS in itself is negative. And what is my IO equals to? IO will be equals to simply VO is minus VS, right? So minus VS minus E divided by R. This will be my IO value. Now IO will be positive. Why will IO be greater than 0? Because minus VS, right, in this whole region minus VS is less than minus E. Okay, minus VS is less than minus E, or I can say that what I can say VS. Just hold on. Minus VS is less than minus E. Sorry, what am I talking about? Just hold on. Because minus VS is in itself positive. Okay, VS is less than minus E actually. VS is less than minus E. So that's why. Or I can say that minus VS is greater than E. Okay, so these two things are happening, and VS in itself is a positive number. Sorry, minus VS in itself is a positive number because VS is negative, right? So my obviously IO will be positive, and again current, so like power will flow from source to load, it cannot flow from load to source. Okay, so these are the cases and these are the waveforms. Just like these waveforms, I hope you understand. Whenever like up until alpha, right, here alpha, all the ACRs will be off. When all the ACRs is off, current is 0, hence the voltage will be E. Once all the ACRs are on, like two ACRs are on, natural pair is on, then in like what will happen? It will follow the input for the positive half cycle, and it will follow the negative of input in the negative half cycle. So this will be T1, T2, and this will be T3, T4. Okay, this will be T3, T4, this will be T1, T2. Okay, here all will be off. Here all will be off. Why? For obvious reasons. Now the current also will just follow, replicate the voltage. Just here one E factor is coming, E is coming, right? That will just shift it down. Okay, and important point note here is that thyristor voltage. So no one draws the thyristor voltage till I did. Okay, to understand intuitively what is actually happening. So in the forward blocking mode, right, this does not exactly follow, each thyristor voltage does not exactly follow the input. Okay, it just follows the half of the input for our assumption, because we have assumed that both the ACRs are identical. If both the ACRs are identical, it will be simply divided by 2. Okay, so this will happen, and when all of them are on, right, when either two of them are on, then what will happen is that it will exactly follow the input, It will, like, the peak voltage will be minus Vm, else it would have been Vm by 2, because they two, like two of them were connected in series. But here, as two of them are on, the voltage blocked by them becomes different. So here, right, sudden change will happen. Why? Because the voltage blocked by them different, because during different periods they are blocking different voltages. Once it is blocked, like once two ACRs together are blocking Vs minus A, and once one ACR it in itself is blocking only Vs. So these two things are different. That's why there will be discontinuity. And why there will be discontinuity, try to understand by yourself. I will not explain this because I've explained a lot of things, so you try to figure it out by yourself. Next, obviously there are currents. So currents, it will be 0 from 0 to alpha, then again it will turn on, again it will be 0 from pi minus theta, because at pi minus theta it will be naturally commutated, then at pi plus alpha again it will turn on. Okay, so these are the current and voltage waveform and expression for average voltage. So remember, again I am repeating after every pi period here, and for a cycle from alpha to pi plus alpha, what is happening? From pi minus theta to pi plus alpha, I am getting a voltage of E. So from pi minus theta to pi plus alpha, I am getting a voltage of E. So that will be, I will integrate with d omega t, and from alpha to pi minus theta, I will get a voltage of Vm sin omega t. So basically, if I divide by pi, right? If I divide by pi, this is one cycle, I will get my expression like this. This is very simple, and IO average will be simply VO average minus E by R. This we have done hundreds of time. And again, if I replace alpha with theta, then control will be replaced with uncontrol, and if all of this formula will be similarly here. Right? This formula is just interesting, and just keep in mind with radians and degrees. So here, right? Generally in gate calculator, by default, if you find cos of some angle or radian, right, cos of theta, some theta, so theta is assumed to be in degrees, but you can change that obviously. But so it's better to know that okay, this is in theta and this is in radians. So these two things are important. Okay, so yeah, now this is the efficiency of the converter. This is very simple, right? POT is PODC IO average whole square plus E into R, and IO is R plus E into IO average. Okay, next is like Vs is equals to this. Vs won't change. Vs RMS won't also change, but Is average will definitely change because it will be equals to 0. Because here, right, I forgot to write here one thing, that in this case is, right, what is my Is? So here some Is is coming. Okay, this IT1 is 0, but IT4 is coming here. So actually my Is equals to minus of IT4, and here what is my IT4? IT4, right, it helps to take the current from the load. So IT4 is equals to simply IO, because whatever current is coming in, that current should go out. So this is equals to IO, but this is like Is is equals to minus IT4, so this will be equals to minus IO, which is again correct, right? So Is is equals to minus IO for one case, and Is is equals to plus IO for other case. So obviously the area, right, the areas of the source current will get cancelled, hence the average source current will be simply 0. There won't be much change. Okay, so there is no DC component, which is why I am very happy. You can see me, I am very happy. Why? Because there is no DC component. We remove the most dangerous component of the on the AC side, and Is RMS will be equals to IO RMS. Why? Because my Is whole square will be equals to IO whole square. This is the reason. Okay, this is the reason why both of them will be equal. Power factor, use the same formula. If the ideal converter, you replace PS with PO and then solve for PS. That's the same thing. Conduction period. So this is very important. What is the conduction period of each SCR? So each SCR is starting from alpha to ending to pi minus theta, because after pi minus theta there is natural commutation. So what is total duration? Duration is end minus initial, final minus initial. So final is what? Pi minus theta. Initial is what? Alpha. So pi minus theta minus alpha will be the conduction period of each SCR. Now let's understand the natural commutation period, right? Just let me turn on the pen. So natural commutation period. So here like it is naturally commutated for pi plus 2 theta. Why is that the case? Because if you go and watch the thyristor waveform, right, it has a period of 2 pi. It doesn't have a period of pi like that of output, okay, or the source current. No, source current also has a period of 2 pi only. So here, once if you observe in this region, right, once this thyris, right, from pi minus theta, so from pi minus theta it is getting naturally commutated because the current is 0. Then for how much longer of time it is less than 0. So here what is happening is that all are off, then they are like dividing the voltages between them, the SCRs T1 and T2. But then as soon as in this pi plus not pi plus theta, in this pi plus alpha, this is pi plus theta, and in this pi plus alpha, what happens? T3 and T4 are triggered. So as soon as T3 and T4 are triggered, that means what? They are turned on, and as soon as that happens, the voltages across the thyristors increases, because now each of them has to totally block the supply itself, not supply minus E divided by 2. So that changes. So it suddenly jumps to this point. I don't know exactly this point. This is just briefly the shape of this. Then obviously it will block the supply, and here again what will happen? Again the SCRs T3 and T4 will be off, and as soon as T3 and T4 will be off, then what will happen is that they will again block lower voltage, because the division of voltages will happen again. T1 and T2 together will block the supply Vs minus E voltage. And at this point, right, what is this point? This is 2 pi plus theta, and at this point this is 2 pi plus alpha. Like this is the point where the voltage changes from negative to positive. What is this point? This is 2 pi plus theta. So I am going from what? From pi minus theta to 2 pi plus theta. My T1 and T2 are reverse blocking mode. Now what is the duration? So 2 pi plus theta minus of pi minus theta. So 2 pi minus pi is pi, and theta minus of minus pi is 2 theta. So that's why this will be the natural commutation period, and this will be the T on period of each SCR. So I hope you understood the point. What is the natural commutation period and what is the T on period? And PK inverse voltage will be Vm, although it depends on like the triggering angle and all those things, but still it will be Vm. Why? Because we'll just assume like as the maximum worst possible case what can happen, and maximum worst possible case across the SCRs, maximum voltage what I can get is Vm, right? Maximum negative voltage is Vm. That's why that's the peak inverse voltage. Now let's start with this. This is just one single example question, and we'll start with full wave rectifiers in the next lecture with L, RL and RLE loads. So let's do this question. A single phase full wave rectifier is supplying a resistive load with R equals to 100 and E equals to 100 volts. So this should be a battery with R equals to 100 and E equals to 100 volts with a continuous trigger pulse applied to the thyristor. So a continuous trigger pulse is getting applied. So if a continuous trigger pulse is getting applied, right, what does this mean? This means that it is like a DC gate pulse. If there is a DC gate pulse, what will happen? The SCR will always be triggered. Okay, SCR will always be triggered. It will behave like a diode. Okay. So given a supply voltage of 230 volts, what is the average value of the output current? So what is happening? We just have to compute like our alpha, right? Alpha becomes theta equals to what? Sine inverse E by Vm. Okay. Sine inverse E by Vm. Okay, alpha is equals to theta equals to sine inverse E by Vm. So what will be this? That is sine inverse. What is E? E is 100 by supply voltage is 230, right? This is given as RMS. So this will be 230 times root 2. Okay. So basically we have to compute average output current. For that to compute, right, what is IO average? IO average is VO average minus E divided by R. So I have to compute VO average for that. So what is theta we get from here? Theta, if I just really compute this real quick, so theta will be 100 divided by 230 into root 2 and sine inverse of that. So theta will be simply 17.9 degrees. Okay, this will be my theta value, and it will conduct till when there is no inductive load here, right? So every cycle it starts to conduct from, like, this is like a diode, right? If it gets converted into diode, it will start to conduct from theta, and it will conduct until what? For a half cycle until pi minus theta, because then everything will be naturally commutated, it will be off. So it will start from 17.9 degrees, and 180 minus 17.9 is 162.1 degrees. So what, this is the form, right? So just you remember the formula or you don't remember the formula, that's fine. You can derive it as well, right? So from alpha to pi minus theta, my devices are on, it is conducting, hence the VO will be simply equals to VS for positive half cycle. And from pi minus 0 to pi plus alpha, because I will be totally computing the average voltage for a pi cycle, the voltage is E. Okay, it is totally from pi minus theta to pi plus alpha. In our case, right, alpha is simply theta. Because this is like a diode circuit. Alpha is simply like theta. So here, if I integrate this, I will get this as a result, because pi will get cancelled. And if I just replace the values, right, if we replace the values over here, this will be 1 by pi 2 into Vm. What is Vm? Vm is 230 root 2, that is 235 volts, almost equals to 235 volts. Cos of theta is 17.9 degrees plus E is what? E is 100 into 2 theta. Remember, right, this theta is in radians. do remember that. So 2 times theta is 17.9 divided by 180 into pi. Okay, so what will be this equals to? Into pi divided by 180. So this is 1 by pi. So this will be 235, like 17.9 cos into 325 into 2. So this is 618.536 cos 19. Have I done it? Have I done cos 19? Yeah, I must have done it. I must have done it. Plus this is what? So this will be 17.9 divided by 180 into pi into 2 into 100. So this will be 62.48. Okay, so this will be equals to what? Plus 618.536 divided by pi. So this voltage will be almost equals to 216.77 volts, and I have to compute the average current. So average current I know, right? IO average will be what? VO average minus E divided by R. R is also 100. So minus 100 divided by 100. It is almost 1.1. Is R 10 or 100? R is 100 ohms only, right? Yeah, R is 100 ohms. So the answer will be almost equals to 1.167 amperes. So this will be the answer to this question, and these type of question comes, right? So like here, right, everything was simple. So it wasn't just about applying the formula. This trick was there, right? Continuous trigger pulse. So you have to identify what is happening. You have to identify the conduction period of the thyristor as well. Okay, so only just applying the formula is not enough. Applying the formula is just one part of the question. Understanding what is happening in the converter, that is also important, right? That's why I always try to focus on the analysis, because if you are able to analyze the converter, right, you will be able to understand these type of questions, because these type of questions will come in gate, not just simply formula application. You have to identify what is alpha, all those things you have to identify, right? So yeah, that's it basically for this lecture, and in the next lecture we'll start with single phase full wave rectifier with RL, L and RLE loads. Okay, thank you for watching, and I will see you in the next lecture.